So chapter 8 goes through and says, at least as far as we're concerned, that 1 mole equals 6.02, it's a big number, times 10 to the 23rd atoms or molecules. Okay. Everybody tends to freak out at that, well, what's a mole? That's a really big number, all of that. Okay, well, what if I had said 1 milligram is equal to 10 to the minus 3 grams? Do you know how to manipulate that conversion factor? Hopefully, yeah. We did that way at the beginning of that semester. Chapter 8, all we're doing is bringing in a new conversion factor. Now we use this new conversion factor. Okay? So it's the exact same principle. It's used the exact same way as we used it at the very beginning of the semester. Okay? It's just now a new term. We have to know what that term means and why we use it, but that's what's coming out of chapter 8. Okay? The next thing that we would look at for chapter 9 as our primary concern is yet a new conversion factor, and that when we go through and run a reaction, we want to know the relationship between our reactants and products. So given a chemical equation, say A goes to B, this equation tells me the relationship between the moles of A and the moles of B. That's all chapter 9 tells you, is now this extra conversion factor. Okay? And where it becomes tricky is that now you have a half a dozen different conversion factors that you can convert all sorts of different directions. Okay? Almost all of your conversions are going to go through moles. And the textbook and even probably questions on the homework and probably on the exam are going to have you go through this, quite frankly, stupid relationship with atoms. Okay? Why would it be pretty nonsensical to work with atoms as far as chemists go? You never work with an atom or even a molecule or even thousands of atoms and thousands of molecules. Cutting-edge technology right now is dealing with thousands of them. We're definitely not cutting edge within this lab or within this class. What we are looking at is dealing with, on the order, I erased it, mole amounts. 10 to the 23rd atoms or molecules. Okay? Because we have to go to such a large scale, that's why we've invented this term of moles, and we try and manipulate everything from moles. Okay? So, lots and lots of dimensional analysis, and I would argue probably the whole rest of the semester is going to be coming back to this dimensional analysis, trying to convert one number, one unit, to another unit. Okay? In almost all cases, you're going to be going through moles. Okay? So it's kind of an important concept to get across, so let's kind of approach it and see what we can do with it. So, start it off. How do we go through and solve this problem? Hopefully you all know how to do this because we did this in class. I know it was a while ago. Where do we start our dimensional analysis problems? With our equals. And what do we know about our final answer? We want micrograms. Okay. What do we do now?
Spend your units.
I've got a unit of microgram. Start with the information we're given. 325 milligrams. Okay. As we talked about before, we would now take a look at our I want to call it reactants and products. Our left and right side of our equation. Is the milligram unit the same as the microgram unit? No, which means we have to do some conversion. Okay? So what we would hope is that at its simplest, we need to get rid of that milligram unit. Okay? So to cancel out the milligram unit, where should milligrams show up in this new conversion? It needs to show up on the bottom so that the units can cancel. And we would hope at best that we could put micrograms on the top. Do we have a conversion factor between milligrams and micrograms? No. Okay, so we need something that's common between milligrams and micrograms. What's the common factor between milligrams and micrograms? Grams. We still want milligrams on the bottom. Why? Still has to cancel. So what we'll do is get rid of the microgram because I don't know how to do that conversion. Okay? What is the relationship between milligrams and micrograms? Or sorry, milligrams and grams? 10 to the negative third grams is 1 milligram. How do we know it was 10 to the negative 3? You memorized that milli meant 10 to the negative 3. Okay, if we look at our units now, our milligrams canceled. Cool, we got that out of the way. And we would look at our units. Does grams equal micrograms? No. So we have to multiply by another conversion factor. Okay, do we want the gram unit anymore? No. Which means our gram in our new conversion factor has to show up where? In the bottom, our denominator. What needs to show up in the top? Micrograms. Why do we want micrograms on top? Where it shows up in our answer. Okay. What's the relationship between micrograms and grams? The micro, I don't think this is one I told you to have memorized, but maybe you got it. 10 to the negative 6. And we could go through, now punch it into our calculator. This is something that tends to give people a hard time, so let me kind of go through the punching into the calculator deal again. What we're looking at is multiplying fractions. Every single one of these terms is a fraction. Okay, well, we've got 3 terms here. Our first fraction is 325 milligrams divided by 1. Okay, so what I would recommend you do for figuring this out is multiply all of your numerator values together. Your calculator will spit out an answer. Write that answer down. How many sig figs should you write in that answer? It's a bit tricky when we're dealing with our sig figs. We would need 3 sig figs as far as our answer goes. If your calculation gave you a whole string of numbers, how many of those numbers should you carry out? Are you allowed to round yet? No. So you should probably carry out an extra 2 sig figs, okay, to make sure that if you have to then shorten it, that you don't lose that rounding information and potentially get the wrong answer at the very end. Okay? Yes?
Are you going to test us on sig figs?
No. We then go through and multiply our denominator. Our denominator should give us 10 to the minus 6. Why did I not include units? What happened to my units? Canceled out, so I can shorthand this and say it's now micrograms. Now I can punch into the calculator 0.325 divided by 10 to the negative 6, and I can get my final answer. Okay? How many sig figs should show up in that answer? 3, because 325 had 3 sig figs. Okay? I will not directly test on sig figs. It might accidentally show up, but I'm going to try to avoid testing you on those sig figs because I just don't think it's all as important. Okay? So this is the idea. Set up where you want to go and what you've got and try and work your way through it. Okay? So let's take a look at a new problem. Farmer has 72 chickens and each chicken lays 2 eggs a day. How many eggs can the farmer collect per day? Okay. Sometimes we could probably crack this out in our head, but let's go through and work it out as far as our unit analysis. What do we want as our answer? We want eggs per day. Okay. What information are we given? We have 72 chickens. We know if we try and convert, chickens does not equal eggs per day. So we've got to do some extra kind of conversion factor here. What's that conversion factor? 1 chicken produces 2 eggs. This is actually a more complex unit here because we also have this happening per day. Oops. So we could then put our day unit down. When we go through and do our math, what happens? Chickens cancel and we get eggs per day. We multiply it out and we get our answer, right? What's our answer? 144. Our farmer can't count above 100. So you tell him 144, he loses his mind, has no idea what you're talking about. Fix that for him. What do you mean divide by 12? So you can explain to him what a dozen is. This grouping of eggs is 12, or a dozen. So you can go through and say, eggs are related to a dozen. 12 eggs equals 1 dozen. Right? So he understands the grouping of those 12 eggs, and he acknowledges that that is now a dozen. So now when you tell him your final answer, what do you tell him? You get 12 dozen eggs per day. Now you've converted his understanding, or that actual number of eggs, into something that he can understand and grasp and deal with. Okay? That's what we're trying to do with moles. Moles is just like a dozen, except instead of it being 12, it's this now massively huge number, okay, which we'll keep coming back to, 6.022 times 10 to the 23rd. Okay, let me write that out. So we get 1 mole equals 6.022 times 10 to the 23rd anythings. The anythings that we're looking at in chemistry would be atoms or molecules. Depends on what we're working with. Okay? Just like I don't have to have a dozen eggs. I could have a dozen bagels, or I could have a dozen people. Okay? It's a number of things. That's the whole idea behind moles. It just happens to be a massive number. Why does it need to be so massive? Atoms and molecules are ridiculously small. So for us to be able to grapple with how to actually run a reaction at a scale that we could work with, we'd be looking at a massive number. Just like the farmer couldn't handle 144 as a number, we can't handle dealing with something that's 4.02 times 10 to the 20th. Okay? So what we do is convert that number into a separate unit that allows us to kind of wrap our heads around the number a little bit better. Okay? Sorry. Mark, did you still have your question?
No, you answered it when you explained the mole thing.
Okay. Okay, and we still haven't even effectively talked about moles yet. Okay, at least their strict application. Okay. Next example that we could go through and look at, see if change things, is we could look at our equations. Okay, so now what we did was briefly talk about the idea of what Chapter 8 is talking about, and now what we're going to do is talk about what Chapter 9 is talking about. Okay? I'm not a very good artist, and I probably should have drawn it on the computer instead of attempting to do this here. Let's make this bicycle. What do we need to make this bicycle? We need wheels, so we can draw on some wheels. There's a wheel. We need the frame. That's close enough, right? Okay. We could go through and say we need the handlebars and the seat, but please bear with me, my artistic talents are really, really bad. So let's just say we need wheels and frames to make a bicycle. If I take a wheel and a frame, do I have a bicycle? Okay. That bicycle is going to have a very hard time moving. If I take one wheel and I attach it to the frame, great. I can now get the bike to move on that back wheel or the front wheel. Or we can try and put it in the middle, but is that our bike? It's not our bike. What do we need to make the bike? We need at least 2 wheels. What have we just done? We made an equation. We made a reaction equation. all of the equations that we've been looking at, combinations, decompositions, single replacements, all of those individual types of reactions are exactly what we're doing here on a much larger scale. Why is it a lot more difficult to deal with in chemistry than it is to deal with in the real world, with bicycles or cars? Because you can see a bicycle, you can see a car. Okay? So you have to kind of translate that information of what you can see and now say you're looking at these at very small scales and kind of pretend that these atoms are shifting around in 3 dimensions in the real world and manipulating them in that case. Okay? So what does this equation mean? To make one bicycle, how many wheels do I need? 2. What happens if I give you 4 wheels and 1 frame? How many bicycles can you make? 1. But I gave you 4 wheels. Why can't you make 2? There's only 1 frame, which brings up a pretty interesting concept. Okay? Again, a difficult one to process when we move down to the smaller scale. Our bicycle frame limited the amount of bikes that we could make. So we could refer to the frame as our limiting piece, or in chemistry, a limiting reactant. What would our bicycle tires be in that example? Okay, if we put up some numbers. If I gave you 4 bicycle tires in 1 frame, just said our frame would be our limiting reactant, because we can't make any more because we're now out of frames. What would we say of our bicycle tires? It's our reagent. I don't know why they didn't come up with a nicer name. In excess. Okay. How much in excess is it? 2. How do you know it's 2 in excess? You processed that equation and said 2 of them disappear to make the bicycle frame. That leaves 2 left over. So you're doing a simple subtraction. Okay? When we move into chemistry, you have to realize that the units we'll end up using are more than likely moles. And because moles are massive, they will be decimal values. Okay? Whereas in this case, we won't see decimal values. Okay? So it does get trickier. But this is kind of the intent of what's happening. So what we've got in our first farmer example is chapter 8. In our bicycle example, we have chapter 9, pretty much summed up in entirety. Chapter 8 gives us a new conversion factor. It allows us to convert between moles and a number of molecules. Chapter 9 allows us to convert between the number of a reactant and the number of a different species. Could be the product, it could be another reactant. So our equation allows us to relate numbers of things. Our mole conversion allows us to convert between the numbers of atoms into a mole. So we can get our reaction into a scale that's easier for us to manipulate and see in reality. Okay? So let's push this into a real situation. How many molecules? So now what we're going to do is get rid of the mole concept and go back to molecules and atoms. Okay? Molecules and atoms are a little bit easier to see because when we look up there, how many molecules of water are there? You see 1. How do you know you see 1? You just see 1 H2O. Okay? So that's a little bit easier to wrap our heads around. So to answer this question, what do we need to make sure we can go through and do? We have to make sure our equation is balanced. Remember back to that bicycle frame equation. Yeah, if we start with a wheel and a frame, we have the components to go together to make a bicycle, but we don't have the proper amounts. We needed 2 tires or 2 wheels to go with the bicycle frame. When we look at this equation, is our equation balanced? I don't think it was it? No. So what do we have to do? Balance. How do we start balancing? How many sodiums do we have on the reactant? 2. How many sodiums is a product? How do we fix that? We need to put a 2 in front. Okay? Now what can we balance? Could balance our carbons. How many carbons do we have on the reactant side? How do you know there's two? I only see one. We also have the CO2. It's the total. How many carbons do we have as a product? Mentioned one. Why are there two? I do only see that one carbon, but the two in front translates afterwards. We have two carbons. Are carbons balanced? Yes. How many hydrogens do we have? Should only see two hydrogens in the product. Two oxygens. Okay, shows up in a lot of places. I was initially going to say three. We have 6 oxygens, and now in our product we have 6 oxygens. Is our equation balanced? Yeah. Okay, so now I'm going to erase everything and clean all that up, bring our 2 back into it. Okay, so we have to realize that that 2 is necessary to go through and process this. So how many molecules of CO2 are necessary to make 2 molecules of sodium hydrogen carbonate? Which molecule is sodium hydrogen carbonate? It's in our product. If I want to make 2 molecules of sodium hydrogen carbonate, how many molecules of CO2 do I need? Where's CO2? In the reactant. What's the number in front of the CO2? 1. How many molecules of CO2 do I need? 1. Okay. Here's where this becomes a little bit more challenging. What happens if I now, let's see, did I ask the right question in the next one? Okay. Now I ask, let's shift this around. Let's say I want 2 grams of sodium hydrogen carbonate. How many grams of CO2 do I need? Switch it up. Let's go back to the bicycle again. I want to make 500 grams of bicycle. How many grams of tires do I need? Can you do that? What does our equation tell us? The number of that species. It says nothing about the mass. Okay? So our equation allows us to base it based off of numbers, but we cannot bring mass into that. Okay, which makes this a little bit more challenging. Our equation can only give us numbers. So if we want to switch in and now bring in mass, we're going to have to do some extra conversion work to get it into a number that I can then relate between these two. Okay? So let's think about mass. What is the mass of 2 molecules of CO2? Yeah, I like where you're pointing. Where are you pointing? Go to the periodic table, and what are you going to do? Okay, mass of carbon is what? 12. What's the mass of oxygen? 16. I add that up, and what do I get? The wrong answer. Why do I have to multiply by 2? There's 2 oxygens. Okay. So now I add that up, what do I get? I'm going to trust you guys. What did you say, 44? Okay, we get 44 what? Atomic mass units. The mass of each of those individual atoms added up. Is this our answer? No, why not? Because I asked for the mass of 2 molecules. 44 AMUs is the mass of what? 1 molecule. So it's 44 AMUs per 1 molecule. If I want the mass of 2 molecules, what do I have to do? 2 molecules, and I want AMUs. What's my conversion factor between, what does that thing say? That says mole. Oh, I was saying molecules. I'm going to run into a problem with that. There's molecules. I want to get rid of molecules on the bottom, and what do I want on top? What's the relationship between AMUs and molecules when it comes to CO2? 44 AMUs equals 1 molecule. What happens if I switch to a different molecule? Then the AMU value changes. What do I have to do? Recalculate it. Okay? How do I recalculate it? Periodic table. Okay? Have that periodic table in front of you so that you can go through and calculate. Okay? So we could go through and do this, and our answer would be 88. We get 88 AMUs. Cool. How do you weigh that amount? We go into the lab, and we've got a balance. The balance is weigh things. How do you weigh AMUs? Does our balance weigh AMUs? No. What does it weigh? Grams. Okay, so an AMU unit was useless. We need to now convert our AMU unit into grams. Okay? So let's go through and now convert our AMU unit into grams. We've got, how many AMUs did we say? 88 AMUs, which is the mass of 2 molecules. So the first part of our calculation is actually already done for us in this. What do we want to get to as an answer? Grams. How do we convert between AMUs and grams? Is there a conversion factor? Where does AMU show up? On the bottom. Why on the bottom? So it cancels. What shows up on top? Grams. Anybody remember that magic conversion factor, which is now about to disappear when I click next? 1.661 10 to the negative 24th grams equals 1 AMU. Oh my God, that's an awful number to have to try and memorize. Good thing we just give that to you. Okay? Punch that into the calculator. What do we get for the mass of 2 molecules? Anybody give me that number? We have a number yet? Still working on it? I don't know what that is. It's a really big number. Probably to the 23rd would be my guess. 2.3. 322 times 10 to the 23rd. Hey, cool, look at that. I got one part right. Well, what's your answer tell you? 10 to the 23rd or 24th?
No, I didn't time to the 10 to the 20, minus 24. I just had 2, like 1.61 had 2.
Times 10 to the 24th.
Oh, I'm sorry. Okay, sorry.
Okay, let's just work with this and say this is fine. It's close enough for what we need. Okay? Go into the balance, or go into your lab, next time you're in lab, and try and measure out this mass for me. How many decimal places does your balance go out to? 0.001, right? That's equal to 1 times 10 to the negative 3. You're missing 20 zeros. Is your balance going to be able to measure this? No. This is the issue with looking at atoms or molecules when we try and run a reaction. We have no way to measure that. It is impossible for us to measure. Okay? So we have to come up with some other way to be able to measure out reagents. If I want to run this reaction up here, I need to mass out sodium carbonate. To mass that out, if I just do a molecule, I don't have an instrument that can get that accurate or that small. So I have to come up with some way to scale up the reaction enough so that my instruments are actually functional. Okay? That's partly one of the reasons we use moles. So what we do is now convert this massively small number, and instead of working with only 1 or 2 molecules, we now work with a massive number of molecules. We work with something on the order of 10 to the 23rd molecules. If I go through and do that, what happens? Now my number becomes 3.322 grams. Can I measure that? Yeah. Okay. So one of the reasons we use moles is so that we can actually do an experiment reliably, measure things out. Otherwise, we're just throwing stuff at the wall and hope it sticks, okay? Which sometimes works. Talk to programmers. Okay? So we can't measure that mass. We're going to have to adjust it some other way. Okay? And that's where we're going to come up with this mole idea. Okay? So Avogadro came through and came up with this and said, you know what? This is ridiculous. Instead of working with just 1 or 2 atoms, I'm going to now work with a massive amount of atoms. I'm going to work with a mole of atoms. Okay? Now when I go through to figure out my equations and figure out amounts, I can get that number up to a reasonable value, or my mass up to a reasonable value that I can now work with. Okay? So that's going to be one of the things that we're going to have to incorporate into our calculations. Okay? So when we go through and look, let's see, did I give an equation? I didn't give an equation yet. So if we looked at the equation, oh, this will be fun. Let's see how good my memory is. We said what? Sodium carbonate plus H2O plus CO2 went to sodium hydrogen carbonate, right? And 2 of them. Now instead of looking at the numbers of atoms, I won't look at the number of atoms. I'll say I'm going to look at a massive number. I'm going to look at 6.02 times 10 to the 23rd molecules of CO2. Okay? If I work with that many molecules of CO2, how many molecules of sodium hydrogen carbonate are produced? Twice that amount. Okay? Why twice that amount? Well, we go back to our equation. 1 molecule of CO2 produces how many molecules of sodium hydrogen carbonate? 2. If I give you 2 molecules of CO2, how many sodium hydrogen carbonate? 4. 6 molecules of CO2. 6 times 2 gives us 12 molecules. Okay? What are you doing in that process? You're multiplying by 2. What if I give you 6.022 times 10 to the 23rd? 2 times that, and I generate that amount. And instead of incorporating that big, massive number, I can now say that that big, massive number is a mole. It's merely the number of molecules showing up in my equation. So if I give you 1 mole of CO2, how many moles of sodium hydrogen carbonate are formed? 2. Okay? So our equation gives us an atom account or a mole account. Remember, moles are just a large number of that. Okay? So that allows us to manipulate and do things a little bit more appropriately for our experiments. So let's try and go through and work a conversion problem here. How many moles of aluminum are in 3.42 times 10 to the 21st atoms? Really don't like this section. There's way too big of numbers. Whew, breathe. Okay, starting with, where do we start our conversions? All conversions. I would argue with our equals. What does this need to equal? Moles. Ooh, good answer on that. It's not just moles, it's moles of aluminum. That's a really important addition. When we're looking at this unit, it's not just moles. It's very specifically the moles of aluminum. In this problem, does it really matter? Is there any other unit or other species to be referencing? No, it's only aluminum, so it really kind of falls off. But what happens if we go to an equation? Okay? If I don't include what species I'm referring to, I don't know how to convert it to another species. So our complete unit must include both the unit that we're used to working with, our moles or our grams, but now also we must specify what we're talking about. So in this case, aluminum. Okay? So that's what we're trying to get to. What are we starting with? Starting with 3.42 times 10 to the 21st. Sorry, I got a little crazy. Atoms of aluminum. Okay? So what we would hope for at first, do we have a conversion factor between atoms and moles? What's that conversion factor? Where do we put the 6.022? I think there's a better way to say that. A good shouting out with the same answer on that, but I would argue there's still a better way. The 6.022 shows up where? In front of atoms. Why in front of the atoms? That's what the conversion factor says. Look where the 6.022 is. It's in front of atoms. It's not in front of moles. Okay? If I go through and change where my atoms and moles are, I could put atoms in the numerator. Then when you all said, oh, it goes into the denominator, you'd be wrong. Okay? Your 6.022 number goes with the unit of atoms, okay, or molecules. So in this case, we could slide in our 6.022 times 10 to the 23rd. And we put our 1 on top. Why do we put the 1 on top? Because it needs to be with our moles. What happens when we do our calculation? So I just yelled that you should have that. I should fix that. Our atoms cancel, and we're left with we can multiply our numerator through, divide by our denominator, and we now have our final answer. It's some decimal value, right? What do you guys get?
0.0056.
I don't know why I decided to bring a 1 in there. 5, 6. Were there any other numbers with it?
7, 9.
Okay, 5, 6, 7, 9. Why did I ask were there any other numbers with it? Sig figs. How many sig figs are supposed to show up in our answer? How many sig figs are supposed to show up in our answer? There are only 3 significant digits there. The 6.022 number, where did that come from? That was your conversion factor that you got to define. Okay, you could put as many sig figs in there as long as they were true sig figs as you wanted. Okay? So our answer needs to carry out to 3 sig figs. Our final answer should be 0.00567, but take a look at our first insignificant digit. What's its relationship to 5? It's bigger, so our answer becomes 568. Yes?
So for the mole conversion equation, would it matter if we put 6.02 or 6.122?
No. I'll try and make sure when I go through and do calculations that I run it with 6.02. For some reason, random digits every once in a while stick in my head. So, okay. Questions about that? Should you memorize that conversion factor? Yes, I will still give it to you. Okay? It is something you absolutely should memorize because you're going to have to use that a lot, okay, particularly for this chapter, okay, and probably for the final as well. Okay? So spend the time to memorize that. Talk to any chemist about moles, and for some reason they get all excited and run around mole day and all sorts of other junk like that. So it is something that chemists, not quite sure why, are excessively proud of. Okay? So it is a number that if anybody says, oh, what'd you learn in chemistry? You're kind of expected to have that number memorized. Oh, 6.022 times 10 to the 23rd atoms is a mole. Whoop-de-doo. Okay? All it is a conversion factor. If you told them that you knew how to convert between grams and milligrams, they're like, oh, that's dumb. But if you give them this number, they're like, oh, wow, that's cool. Okay? Questions on that? Let's try another one. How many oxygen atoms are in 0.24 moles of O2? What's our answer need to be? Moles of oxygen atoms. What's our symbol for an oxygen atom? O. Is that going to be important? It's going to be pretty hugely important, so we've got to be careful with this one. How many Why did I say moles?
Yeah, it should be atoms.
It needs to be atoms. How many oxygen atoms are in 0.240 moles of O2? So what do we need to start with? 0.240 moles. Okay. Of oxygen, I kind of accept, but I want to get really, really picky on this because that 2 is really important. Why is it important? If we compare across this equation, our unit on our left says O2. What does the unit on the right say? O. We have to account for that difference. Okay? And we can account for that difference in a couple different ways. So, where do you want to start? What unit do you want to address first? Okay? Where should moles show up? Why in the bottom? You need it to cancel out. What should show up on top? We want to stick with units first. Atom refers to what? I know that's a very dumb question. Let me try that again. An atom refers to a single atom. Is O2 a single atom? No. What is it? It's a molecule. So what we're looking at is the molecule of O2 and moles of O2. What's the relationship between molecules and moles? 6.022 times 10 to the 23rd molecules. Our conversion factor only says atoms, but that can be molecules. Does that say molecules enough? Okay. And we put our 1 down below. Evaluate our units. What happens with our units? Moles cancel. What would our answer be at this point? Molecules of O2. What's our answer in? Atoms of O2. Is that correct? Nope. What do we have to do? We're going to have to get rid of our molecule unit, so it needs to show up on the bottom. Molecules of O2 to atoms of oxygen. Oh, crap. Another conversion factor. What's the relationship between molecules and atoms? Oops, sorry. How many atoms of oxygen show up in a molecule of O2? How do you know there's 2? The said so isn't quite correct. Look at our subscript. Our subscript shows a 2. What does that 2 mean? There are 2 oxygen atoms. 2 atoms, 1 molecule. Okay? So not only do we have to understand our moles and molecules, okay, and the relationship back to atoms, but we also have to incorporate a conversion factor that relates to our formula. Okay? Just like we did with our equation, we could compare molecules across an equation. A formula allows us to compare how many individual atoms are in it. That's how, when you went into the lab, you were able to calculate the percent hydrate in that sodium chromate water thing that you guys had to do a couple labs ago. I just graded it, that's why I know. Okay? It's dealing with what those numbers mean. Questions about it? Yeah?
So how many sig figs would you answer?
Oh, good call. Sig figs as far as our answer goes. What do you guys think? Can go through and evaluate each of our values. This is 3 sig figs. What's the next one? Okay. We could go 3 or 4. Okay. If you don't remember that extra 2, then you're stuck with 3 sig figs. What's the next one? Everybody's favorite answer. It's infinite. Why is that one infinite? There are exactly 2 atoms in 1 molecule and exactly 1 molecule of O2. Just like when we look at a bicycle, there are exactly 2 tires. There aren't 2.5 tires in a bicycle or 2.3 tires, it is exactly 2, which means that conversion is infinite. So now when we go back through, what is our fewest amount of significant digits? 3, which means our answer needs to be reported to 3 sig figs. Will we still get a decimal in this case? Yeah, why? Because you're multiplying by 10 to the 23rd. So officially we don't have a decimal if you carry that 23rd out. Okay? It'll actually be 10 to the 22nd probably. Why did we bring in molecules? What did we start with? A molecule or an atom? We brought in molecules because we started with a molecule. Why did we have to convert to atoms? Because it asked for us to convert to atoms. Okay? If I had asked how many oxygen molecules are in 0.240 moles of O2, all we have to do is eliminate that green calculation at the end because we're already in molecules at that point. Okay? So you have to be very careful to answer the question that's asked and start applying your information systematically into it. Okay. I was just guessing based on the, oh, it should go, no, it should have been that, isn't it? Oh, 0.4 times 6. No, you're right. It is still 20. I started trying to do it in my head. It didn't work. You're right. It should be 23rd. Okay. This is why you have a calculator. I'm not a human calculator. Okay? Questions on it? Okay, so we could look at a mole of several substances. So your textbook gives you this. Kind of an interesting figure, though the sugar one looks kind of cool, because you can't see it at all. Are all of those amounts the same? They all weigh different things. Why would they be differing amounts? Has to do with density. Has to do with the mass of each of those particles too. How do those things interact and pack together? You will get different volumes for an individual mole of solid substances. Okay? Because they're going to interact with each other slightly differently. Okay? As a change, so we can try and predict what's going to happen after we do the exam, what happens when we move into a gas? Would we expect the atoms to interact with each other? In the gas phase, we've completely removed them away from each other, which means the atoms do not interact. Which means, what would we expect for the volume for any gas, a mole of any gas? It shouldn't change. We should expect the exact same volume for every mole of gas, regardless of what type of gas compound that is. Okay? And that's because in our definition, we assume that the particles do not interact. The reason we get different volumes is because the particles interact. Okay? Turns out to be true. You don't need to know that, but it is showing up, or at least for this exam, does show up in Chapter 8. Okay? So, mole calculations, remember, the whole reason that I went through and said we needed this was because we were trying to figure out mass. Get a mass of our reactants to be able to apply. Okay? Everything we just went through and did, we converted atoms into moles, but we really didn't bring mass into it. We wanted a mass. Okay? Well, it turns out Avogadro's number can indirectly actually get us some mass information. And we can cut out one of those steps that we were looking at. Okay? What is the mass of 1 mole of protons? That's the number of them. What's the mass of a proton? 1 AMU. Okay? But if we want to get that into grams, we'd have to use that 1.66 times 10 to the negative 24th gram value. Since you guys got your calculators, well, since one of you has calculators out, go ahead and take 1 divided by 1.66 times 10 to the 24th, negative 24th. What do you get? So So I'm asking for 1 divided by 1.66. Is that right? Times 10 to the negative 24th? Was that the conversion for grams? What's your answer? You got to be careful. Look at where your 10 to the negative 24th is happening. It's in the denominator. You put it up in the numerator by accident. 6.02 times what? Times 10 to the 23rd. Where did you got to be careful with where you're putting your 10 to the 24th. I'm telling you right now, what you're doing is multiplying by 10 to the negative 24, not dividing. So show me your calculator after class, and I'll show you specifically where you're putting it. You're putting it into the numerator, not the denominator. It gives it to your answer at 6.02 times 10 to the 23rd. 10 to the 23rd. What was that number? That was Avogadro's number. When we converted AMUs to grams, we were unintentionally using Avogadro's number. What can we do with that information? Okay, what happens if we look at a mass of a mole of carbon atoms? Okay, so 1 mole equals 1 mole of carbon. Okay, right now the only mass unit we've got are what? AMUs, right? So how can we figure out the mass? Okay, we can go back to our periodic table. We'd have to convert our moles into atoms. Oh, shoot. Didn't give myself enough space. 6.022 times 10 to the 23rd. Our moles cancel. We now have atoms. Using our periodic table, what's the mass of 1 atom of carbon? .01 AMUs for carbon. Okay, but we don't want AMUs, we want grams, right? So let's convert it into grams. AMUs to grams. What was our conversion there? 1.10 to the negative 24th was 1 AMU. What does that give you as an answer? What? What does that even mean? Why is it 12? If I want to know the mass of 1 mole of carbon atoms, what did it equal? The atomic mass directly off the periodic table. Instead of now looking at our periodic table and seeing atomic mass units, it's actually the mass of that atom per mole. It already involves my conversion factor of mass and atoms and Avogadro's number. All of that is already incorporated into our periodic table. So if I want to figure out the mass of carbon atoms, instead of doing all of that work, 1 mole of carbon atoms, I have a conversion factor between moles of carbon and grams of carbon. What is that conversion factor? Periodic table tells me that there are 12 grams per 1 mole of carbon. What's my answer? 12. I didn't need to use anything fancy. I didn't need to use my Avogadro's number or anything else. That's because the numbers on our periodic table are not just AMUs. We can use them to get grams per mole, which is why our periodic table becomes vastly more helpful, because we now have a way to convert between moles and grams without having to do a slew of extra calculations. Okay? So that whole atom argument on trying to convert between mass of atoms and all that other fun stuff, irrelevant. We don't give a crap because we measure in grams and we look at things in moles. All of that information is already on the periodic table. What is the mass of 1 mole? Well, let's switch it up. Let's do 2 moles of CO2. 2 moles of CO2. Our mass needs to be in grams, CO2. What are we given to start with? We're given 2 moles of CO2. Can we convert moles to grams? We can convert moles to grams of CO2 using our periodic table. So what we can go through and do is add up the weights for carbon and for oxygen in a mole. So carbon's gram per mole is 12. What's oxygen's? How many oxygens are there? Gives us 40, you said 4? Grams per mole. Okay, where does the 44 show up in front of? The grams. So we put, what number shows up in front of the moles? 1. What happens? Moles cancel, and what do we have? Grams of CO2. Did we see Avogadro's number? No. Did we see the mass conversion between grams and AMUs? No. So this all-important, powerful number of Avogadro's number, so crazy and cool and important, for every calculation that you would ever really need to do, you never use. Okay? It underlies the basics of how we can interpret or convert our atomic understanding on the periodic table up to something that we would measure and weigh. So it is vastly important as a background conversion factor. But as far as an everyday use in chemistry, useless. Almost. Okay? So we would end up, in this case, with the answer of 2 times 44, 88 grams of CO2 in 2 moles of CO2. Okay? Kind of neat. Okay? So, big conclusion from that, the atomic mass on the periodic table is used as the molar mass, which means our mass, units for mass, grams, units for molar, moles. So if I want to be able to convert between grams and moles, I can use the periodic table, because that's a fun way to say it, to figure out the molar mass, and now I can convert between grams and moles. Okay? Hugely important conversion. You will do that one for the rest of your life in chemistry. Okay? If you're not in chemistry, well then, let's just say you'll do it for the rest of the next 5 weeks. Okay? I think it's a little bit less than that, actually. Okay? So, conversion factors. You're looking at Avogadro's number. That allows us to convert atoms to moles. Atoms are effectively the same thing as molecules. It's a count, a number of something. So Avogadro's number gives us atoms to moles and molecules to moles. Our molar mass will give us grams to mole. Okay? I could go through and put in numbers for some of these. Most of them I can't put in numbers for. Why not? In fact, the only one I can give you a number for is Avogadro's number. Why do I not give you a number for molar mass? It's different for every element. It's different for every compound. You have to calculate that gram to mole relationship. How about the balanced formula? That can give us atoms to atoms, but like we said, atoms were virtually useless. It gives us moles to moles. Why do I not give you a number there? Every balanced equation is going to give you slightly different coefficients. You're going to get slightly different mole-to-mole ratios. Okay? The last one that could kind of show up there, which I would put kind of as a cheaty, though in my opinion it's a long, excessive way to go through and process it. You can do grams to AMUs or AMUs to grams using that 1.66 number. Okay? The only reason I know 1.66 is I've now had to say it like 6 times. Yeah, I said 6 again. Okay? Chapter 9. Whoops, that was supposed to shift out. Oh, this says balanced formula. Chapter 9 says balanced equation. This allows me to convert molecules to molecules or moles to moles within an individual equation. And effectively moles of one species to the moles of another species. Okay? In summary, that is what will show up on your test. You can be expected to look at least one type of conversion within each of these and potentially a string of them. So if I give you grams of reactant A, So let's say we look at a reaction A goes to B. Actually, let me check. Did I put this on the next slide? Did not. A goes to B. If I give you grams of A, and I ask for grams of B, okay, do we have a way to convert between the grams of A and the grams of B directly? No. Where are you getting 2 to 1 from? Where'd you get the number 2 from?
1 to 1.
Where'd you get the number 1 from? Pulling it from the balanced equation. That 1 and that 2 refer to what units? Atoms or moles, not mass. If I ask you to build a bicycle, if I give you 2 wheels, you're like, okay, sure, I can do that. If I give you 100 grams of wheels, I don't know, can I actually get an actual bicycle out of 100 grams of wheels? Okay. It would depend on some conversion factor. So if I start with grams of A, I need to convert the grams of A into moles of A. Once I'm in moles of A, I can now convert A into B using the balanced equation. So I use my grams to moles to moles, and then moles to grams. I have to go through 3 separate conversion steps to convert all the way across. Okay? So we can string several of these together, evaluate at each stage, and remember what your conversion factors allow you to do and where they come from. Okay? Molar mass. Do we need to see that calculation? We run this example? Or do you think you guys got this one? How do you figure out the molar mass of copper nitrite? Molar mass is something that is found where? Periodic table. So what do we have to do? We look up the molar mass of each of the atoms that show up within this. So we would take the molar mass of copper plus the molar mass of nitrogen. Someone said something else there. What was that something else you added? Times 2. Why did you multiply by 2? There are 2 nitrogens in copper nitrite. Plus the molar mass of our oxygen times 4, because there are 4 oxygens. We now add those molar masses all up, and we have our final answer. So use the periodic table to determine your molar mass. Yes?
For a test, do you want us to use, is that okay, we just do that, or do you want us to do like regular?
I don't know what that means. For show your work?
Yeah, for show your work.
For show your work, I wouldn't ask this question right off the bat. Okay. The only reason why is that most people, if you understand what's going on here, what do? You pull out your calculator where you can see everything you typed in. You look at your periodic table, say copper is 63 plus nitrogen 14 times 2 plus oxygen 16 times 4 equals, and you write down an answer. To show your work takes you more time if you actually know what's going on. If you don't know what's going on, then it helps. Okay? This question doesn't prove anything as a show your work problem. Yeah?
The units will actually be moles per gram.
What are your units off the periodic table? Iron, the molar mass is 55.85. It's the molar mass, so we're concerned primarily about mass. The number given off our periodic table is the mass per mole. So if we looked at iron, the molar mass is 55.85 grams per 1 mole. Okay, the unit off your periodic table is always grams per mole.
So if it just asks for molar mass, that's what you want.
That's all I would need, the grams per mole. Okay? Let's try a mole to mass. So now, would have been nice if I'd written down the answer on that one. What is the mass in grams of 0.532 moles of copper nitrate? So we start with our answer. Our answer needs to equal, whoa, come back here. This equals grams our copper nitrate, what did I do? nitrite. This one gets an extra little bit tricky. Why? It didn't give you the formula. You had this question tests both your conversion ability and nomenclature all at the same time. If you don't know how to do your nomenclature, you can't show me how you go through and do your conversions. Okay? What are we starting with? 0.532 moles of our copper nitrite. Do we have a conversion factor between moles and grams? 6? What?
6.
We would do our molar mass, which is what relates our grams to moles. So we'd have to add it up. Our copper is 63.55 plus 2 times our 14 plus 4 times 16 equals, what's that? Yeah. Look at 16. Carry it out 2 decimal places. Or oxygen. Carry out the molar mass of oxygen 2 decimal places. What is it? 16.00. What are you going to write on your test? 16. Thank you. Yeah. That's why I asked oxygen. What's our total come out to? 155 grams per mole. The 155 is in front of grams, 1 mole. Do our math and crunch it out. For those of you pushing me on the sig figs, you're absolutely right, which is also absolutely why I don't ask you sig fig questions anymore. Crap, that was recorded. I absolutely do. Okay? Questions on that? What is the, I hate these. Mass in grams of 2.55 times 10 to the 23rd atoms. How do we set this up? We need grams of our lead. What do we start with? 2.55 times 10 to the 23rd atoms of lead. Do we have a conversion factor that relates our grams to atoms? Really? What's that conversion factor that relates grams and atoms? Periodic table gives you 2 things. There's 2 possible units your periodic table gives you. Your molar mass, which is grams per mole. Is that grams per atom? No. The other thing it gives you is the atomic mass, which is the mass per atom. And what's your unit on the mass per atom with your atomic mass? AMU, not grams. We don't have the conversion between grams and atoms. Okay? So what we're going to have to go through and do is one of 2 options. Okay? We can either convert our atoms into moles using Avogadro's number. What was Avogadro's number? 6.022 times 10 to the 23rd. What's the unit on that number? Atoms equals 1 mole. Okay, so we put our Avogadro's number down below. So it's not just memorizing the number, it's memorizing the unit that shows up with that number. Just like you had to do with all your other conversion factors. Once you've got it into moles, then what could you do? Now you can do the molar mass off the periodic table. Okay? Or we use our AMUs per atom, and then we could go through and convert AMUs to grams. Okay? Both methods work. And since you asked me to fill it out, lead, molar mass, why can't I find it? Thank you. Now I don't have to find it. or 207 AMUs per 1 atom. And then it was 1.66 times 10 to the negative 24th grams was 1 AMU. Test it out in your calculator, you'll get the exact same answer, either way you go at it. Okay? Which could be another challenging thing. Realize there are multiple ways to go through and solve this. Does it matter that I do the 1.66 after the 207 or before? Why does it not matter? What's 2 times 1? What did I say, 2 times 1? What's 1 times 2? 2. Does it matter which way I multiply? No. What will become really, really important, as you guys already saw, is that you make sure that you put that value in the proper spot. In our first equation, what happened? We are dividing by 10 to the 23rd. In our second equation, we are multiplying by 10 to the negative 24th. You have to make sure that you enter it into the calculator properly. That is going to be the biggest and hardest or easiest mistake to make that will happen consistently. So those of you that kept getting the wrong answer when we tried to convert that 1 divided by 1.66 thing into Avogadro's number, talk to me after class, show me what you're entering into the calculator so that I can make sure that you're fixing that mistake, that you don't make it again. Okay? More calculations, more calculations. There's your conversion factors. The last one that I really want to address before we take off, I won't ask a whole lot of questions on it on the exam because we didn't talk about it a lot, is that balanced equation. That allows us to convert molecules of one species to molecules of another, or moles of one species to the moles of another. Those are equivalent conversions. Why are they equivalent? What is a mole? They're the same idea. A mole is just a larger number of molecules. It's still the same type of conversion. Okay? Was hoping to get through to the textbook's version of this. Making cheese sandwiches. Okay, that's what the textbook decided to use. I think bicycles are more fun than cheese sandwiches. So you can look at the textbook's example for limiting reactants. You can expect to see a question on limiting reactants. Not a calculation, okay? But being able to look at it and say, yes, that is the limiting reactant species, or that is not the limiting reactant, or that's the one in excess. Okay? So use the information from a balanced equation to decide what's in excess or what is limiting the reaction. Okay? If you've got questions, just stay after class and I'll help you with it.